right, so today is what is consensus analysis? We'll get right to it. Usually when we take measurements, most social scientists recognize that we aggregate across people. This reflects our concern to know about variables rather than about people. What goes with what? If income goes up, does education go up? When we aggregate across people, there's something else going on, and that's what consensus analysis is. We assume that there's consensus, but of course we know that there's variation. If we ask 100 people who make the name the football team that has won the most Premier League championships, then people who know the answer will agree with one another. People who don't know the answer will guess, and because there are many choices to guess from, those who guess the answer will agree with one another less than those who do know the answer. The cultural consensus model formally lays out the condition under which agreement implies knowledge. And we can test the relationship between agreement and knowledge by looking at the results of a university exam. Suppose we give 100 students a 50-item exam with questions like this one. So, which of the following is best known for his or her contribution to function? There's an answer. The answer is number 4. All the people in social science who studied this know the answer. And there are 5 choices. It's a very typical question. Now, each student makes 50 choices of a number between 1 and 5, one choice for each of 50 questions. So you get a vector of numbers, right? A simple line of numbers, just like anything else you would, a profile matrix, a line of numbers. And you can compare the answer, that line of numbers, to the answer key. Now the answer key is the vector of numbers produced by the instructor who gave the exam. So here's 25 answers from one student to a 50-question exam. So here's the first 25 questions. Here's the student's answers. We can imagine that there are 50 or 100 of these lines of data, one for each student. And the way we typically do this is we take this and match it. We do a matched coefficient test. Does this answer match this? The answer is yes, 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 no. Okay, so we add them all up. We take the number the student gets right, we divide by the number of total possibilities, and we get a percentage. So the answer to that question was number 4. And we, in this particular case, the student got 39 hits, or 39 out of 50 questions, which is 78%. Now, what we've done is to run a test to find the similarity between 2 vectors of numbers. In this case, it's called the matched coefficients test. There are many such things you could run. You could run, for example, a Pearson's product normal correlation. But the problem with that is that if the answer key has 5 and the student answers 4, the student gets credit for almost being right. Right? So we don't use that. There are many ways in which you can compare vectors, but this one would be a matched coefficient, and that would produce a percentage. And we can't, we don't take the 78% on faith. If we wanted to know how much the student knows, then we would have to not take the 78% on its face value. We'd have to see, we have to adjust this for guessing. And that comes from classical test theory, from psychology. So this is from Steve Borgatti's site. Actually, it's a wonderful site, and I highly recommend it. So the answer is, does the student know the answer to this question? If the answer is yes, with probability D so high, then write it down. Does she not know the answer? It's 1 minus D so high. In that case, guess. What's the probability of guessing right? Well, the probability of guessing right is 1 over L, where L is the number of possible choices. In this case, there are 5, so it would be 20% chance of getting it right. And the wrong answer is L minus 1 over L, which is 80%, right? So this is the right answer, which is probability of getting the right answer if you guess. And this is the probability of getting it if you know it. Now, there are two equations, one expressing the probability that a person answers a question correctly, and one expressing the probability that two people agree with each other on the answer to a particular question. So the probability for student I of getting a particular question right is, as we just saw, d sub I plus 1 minus d sub I over L. So that they know it, adjusted for the probability of guessing. Hold this in mind. This is classical testing. This test you've taken all your life. Probability of getting the answer to a question right. You know the answer, or you guess, adjusted for the number of possible choices. So in a true-false test, the probability is 0.5. You know, multiple choice test with 5 answers, there's 0.2, right? And so here's how we would do it, actually. We would say knowledge would be the original score, L is the number of choices. So in this case, the students, we just simply adjust it. And the student's knowledge, we would say, is probably about 72%, even though she got 78 on the test. Now the second equation is the probability that two people, I and J, agree on the answer to a question. Remember what we've done just now is we've taken the probability that the student's answers agree with the truth, where the truth is established as the professor's answers the answer to, right? Well, now we're going to do this again for every pair of people. So if there are 50 people, there's 50 times 49 divided by 2 possible pairs. N times n minus 1 over 2 pairs, right? And the second equation in the model is the probability that two people agree on the answer to a question. Not that two people, I, and where J is always the professor. But any two people, right? Okay. Now there are 4 ways for this to happen. I and J both know the answer with the probability of D, and so they answer the same with the probability of D sub I times J. So if you have a 90% probability, you get a 90 on the exam, a 90% probability of knowing the answer, and another person has a 90% probability of knowing the answer, they get the same answer with 0.9 times 0.9, 0.81, with an 81% chance of getting the same answer, right? If they both actually know the answer, that's probability 1. So then they get, then d sub I, d sub J is 1 times 1, which is 1. Now, the other possibility is that the first student knows the answer, the second student doesn't, but guesses correctly. So they get the same answer. The third possibility is that the second student knows the answer, but the first student guesses correctly. So they get the same answer. And the fourth possibility, which is a little teeny probability, but it's still in there in the equation, is that neither of them know the answer, and they both guess, but they happen to guess the same answer. Could be a wrong answer, but they guess the same. So this is the, add these sums up, add these up, and you get the sum probability that two people get the same answer on an exam, on a question, right? So the probability that two students give the same answer to a question is the sum of these 4 probabilities, and here they are. The IDJ plus 1 minus the IDJ per L. Now, if you recall, just in case you didn't, look right here. Look at that. So here, the probability that we get the same answer, this is the total probability that student I, student J get the same answer to any given question. And the probability for getting a question right is that little piece right there. Take a minute. to absorb that. What do you see? Same question. They're virtually the same. They are related. They are highly related. This is what the great advance is. So what does that mean? It means that given certain assumptions, right? Well, we'll take for granted that the test that you give is made properly. The answers are all the students independently answer each one. They're not related to each other. There are certain assumptions that you have to make. Okay, fair enough. Given assumptions, agreement and knowledge are related. Now, turns out we can actually find the level of knowledge of each student in a group if we know the level of agreement among all the students. That's what that means. It means you can lose the answer key. Given that you meet the assumptions, you can lose the answer key and retrieve it by finding the level of knowledge of each student. And you find that by doing what? Running a matched coefficient similarity test on two vectors, right? And factoring the agreement matrix. If we factor the agreement matrix for all the members of the group, what we get back is the competence scores, the IDJ for each member of the group. Why? Well, suppose there is what you really want to test here is that there is what we call a single factor solution. Operationally, this means that the eigenvalue, the first eigenvalue is relatively large compared to the second. Heuristically, it means at least 3 to 1. If the first eigenvalue is at least 3 times the size of the second, you have effectively a single factor solution. It means that one factor is accounting for at least 2/3 of the variance in the matrix. At least 2/3, one factor. Now, if you've ever done any factor analysis, you know that you get a bunch of factors that each account for some chunk of variance. You don't really find factor analyses that have, unless you set them up properly, that you're going to have at least 2/3 in the first factor. But that's what you're actually setting up here. If it's a good test, if it tests the knowledge, if people answer independently, and then the agreement we've seen should relate to knowledge. So if we factor it, we should get back a single solution, single factor solution. Name the factor. Well, the factor is knowledge. Nothing in all of science is more qualitative than watching a bunch of scientists sit around the table looking at a factor analysis and saying, what do you think we should call that factor? Oh, I think that's the whatever factor. Yeah. It's a Rorschach test, right? But we know in this case what it is. It's knowledge. So here, I actually ran this. Are you prepared for this? Be prepared. You don't see that much in social science. So I ran 160 students, the dots, right? And this is their cultural consensus model score. First, they're loading on the first factor, right? And here's their actual grade on the test when I compared their, actually derived their against my answer key. That's the relation. I could throw away the answer key and retrieve it. I could have given every student that score that they got and never have cheated a student by more than a half a grade, a B plus maybe instead of a B. In no case. In almost all cases, it was entirely right, dead on. Now, that's important because in fieldwork, that's what we do. If you ask people about medicinal plants and what they cure, what are the causes, the signs, the symptoms, the response to the cures for a set of illnesses, that's what you're doing. You're assuming that there's a set of answers, that there is a truth out there is a cultural truth. Some people are more competent than others. You really want to find out which ones they are. You want to interview them because they're going to be your best informants about that topic. So, we're not talking about general cultural knowledge and chief informants in the field. We're talking about domain-specific informants. People who know a lot about teams in the Premier League who win football matches, about medicinal plants, about movie actors, about any set of items in the domain, any set. There is an answer key. We want to find the answer key, and we want to interview the informants who are best at it. That means we can do this. It's a godsend, by the way, for field workers. It's a godsend because it also means that we don't need large numbers of people. Where there is cultural consensus, and we can establish that, it means that we can interview a very small number of people and find the answers. So all of our sampling issues vanish when you have tested cultural consensus. So, assumptions. The model works when there is an answer key. People respond independently. Each person has a fixed competence at the time of the exam, and the questions are all equal difficulty. Now, there is an answer key. That's a tough one. It means there's a single truth, one and only one correct answer to a question. If there are several truths, men and women, for example, or old people and young people have radically different and correct answers to a question, then there's no cultural consensus. But this will show up in the analysis with two or more factors instead of one. So while the assumption is strong, it's the strength of the model. Because there are two sources of intercultural variation. One is competence. People are simply better at knowing about football or medicinal plants or political fortunes of politicians in the country. When there's a single cultural truth for a cultural domain, people who know more of the truth are simply more competent. But another source is the existence of subcultures. Men and women, old and young, shamans. They have very highly specialized knowledge about wild plants, but in the test of knowledge about those plants, they would show up as incompetent because they would give answers that would be completely different than everybody else. So when I say shamans, I mean, in general, people in the financial industry are shamans. They have knowledge that they control. If you ask them about it, they'll be cagey. They'll give you answers that are different from everybody else. You won't be able to extract very easily because their knowledge is potent. So one of the very useful things about this model is it helps us find out if there's a single cultural truth or several of them, and lets us estimate the number of informants needed in a study of a cultural domain. Because depending upon how much consensus there is, that changes the number of people you need in order to be able to describe the domain well. So if there's 100% consensus on all the contents of a cultural domain, what are the names of the months of the year? Ask a bunch of people do the same answer over and over again, right? So it's like, it's exactly the same thing as how much of a soup do you need to sample in order to know whether it has enough salt. Well, it's thoroughly. You take one drop, one spoonful, and you get it. It's all in there. Everything you need is in one sample. Waller and Rodney calculated the number of people you need to produce valid and reliable data about particular cultural domains, given that the three conditions of the model are more or less met. Here it is. It's a difficult to read slide, but you can see this. It'll be there. It's from a book of theirs from 1987, I think, 88. But you can see, look. See that? Look. Average level of competence, 0.7. Proportion of questions, 95, getting right, 99% proportion with the 95% confidence level, 10. 10 informants. 10 informants with an average confidence of 0.7 have a 99% probability of answering each question on a true-false test correctly with a confidence level of 0.95. pretty dramatic. I mean, if you were an anthropologist, you'd say, gosh, this is a lifesaver. I no longer have to justify to all of my psych and sociology and political science colleagues why I'm using so few informants, because I'm systematically getting informants who know a lot about this, and I've tested them for it. This model has been used in the study of beliefs about symptoms of AIDS, diabetes, the common cold, the causes of breast cancer, comparing Mexican and American women and what they understand to be the causes of breast cancer. It's a long list of questions, true or false, ask people the answers. We have a test. Right? How do you get those questions? Well, you extract them from the ethnography, from what you know about in depth. But you can do this for anything. It's been used to study indigenous plant knowledge, psychological constructs, social support. What do you need in order to be able to get through life? What kinds of support are needed? It's a perfect thing to do for that kind of network analysis. It's been used to study reader accuracy in judging X-rays. In sociology, it's been used to measure social class rankings of occupations. Here's a list of occupations. Tell me, which is the most prestigious? Oh, everybody gets a list of the occupations. You get a big long list of the rankings. For each informant or respondent, you have a vector. You get a big long list of the informants. Well, you can see, everybody agreed you only need one. If there's variation, you need more than one. You can test that. You can test the extent to which there is variation by simply getting the agreement matrix and factoring it. You can see it was developed in anthropology and psychology, but it has uses everywhere. And by the way, you should know that it comes from a very long and noble intellectual history on what you might call wisdom of crowds. Right? The first paper in that intellectual history was the Marquis de Condorcet in 1785, famous jury theorem, the probability of reaching a correct verdict if you had more than one person. So when would you want a judge, and when would you want a jury? Right? Oh, if there were a lot of disagreement, you'd want a judge who knew a lot about it. If there were agreement that if the probability of reaching a correct decision was above 0.5, you'd want according to that theorem, you'd want a jury. Well, now we know that it's not just the probability of reaching a correct decision, but under certain conditions, it's the probability of having people agree on the same decision, which under certain circumstances you can imagine could be a totally incorrect decision, right? Which would be an interesting set of cases to examine, but it wouldn't invalidate the principle. Much later, Francis Galton, wonderful paper in 1907, went to a fair in Plymouth, and there were 800 people who bought raffle tickets and guessed the weight of an ox that was on raffle. Right? So he had the 800 raffle tickets, and he had the guesses that they went. And the guesses ranged from about 1,100 pounds, about 1,000 pounds, to about 1,700 pounds. The mean was 1,196 pounds. The actual weight of the ox was 1,198 pounds. So Francis wrote this wonderful paper about agreement and knowledge. Right? This is part of the grand tradition of the wisdom of crowds. Robin Dawes, a psychologist, asked 25 of her colleagues at the University of Oregon to rate all the other 24 on their height. Right? Not how tall do you think they are. Oh, 5'11", 5'8". No. Rate them on a scale. 1, 2, 3, 4, 5, a Likert type scale. Right? And she did it with 5 different scales, semantic differential and liker type, and right? Well, it turns out that the score on the factor of the first factor of the accumulated scales correlated 0.98 with the actual height of those 25 people. Again, the wisdom of crowds. So we have lots and lots of cases like this, and the last one would be, I think, Jim Boston, when he did his doctoral dissertation in Peru. He walked 61 people through women through a garden with 61. Let's see, I can't remember how 58 women, but there were, I think, 61 types of manioc in the garden. And he asked each of them, "What's that? Name that plant." Now he knew because he planted the garden. So he had the answer key, right? Then he calculated the probability that they got the answer right, depending upon whether they agreed. That was one of the things that led immediately to the breakthrough on this as well. That plus the fact that if you look at the original paper, it was called A Theory of Culture and Informant Accuracy. It was in, some of it was, because me and my research partners and I had given some data to reanalyze on informant accuracy. But anyway, it's an entire tradition on the wisdom of crowds in accuracy of reporting. And the consensus model is a formalization of everything we've known about that. It's a big, big breakthrough, in my view, because it means you can lose the answer key, which is essentially what we do in almost all social research where we're studying the content of the cultural domain.